Okay, so in this lecture, you will be solving uh, frame analysis, sway analysis of a frame, pero you will be using beam matrix formulation. So, halimbawa, this is a 1, 2, 3, 4-story frame building, and these are the properties. I have a say hypothetical 300 by 500 concrete column and loaded with lateral force from your earthquake load, diba? For example. And then okay, concrete, but for the girder, I assume a large cross section because remember, in reality, this frame is, ang assumption natin dyan is actually rigid. Okay, so actually rigid siya and we are avoiding rotation. So basically, ang assumption natin sa sway niya is something like this. Okay, so say this is delta 1, this is delta 2, this is delta 3, this is delta 4. But walang rotation to. So translation lang ang assume displacement natin dyan. Okay, so ganun din dito. Pag nag-sway to, this is delta 1 also, delta 2, delta 3, delta 4. Now, for a typical earthquake loading, lateral load, it is expected na ito yung pinakamalaking lateral displacement, di ba? So, then ito yung pinakamaliit, yung delta 4. Okay. Now, we will assume a beam matrix formulation for that. Okay? So, parang yung ano natin, yung derivation natin sa beam stiffness, something like that. Okay? Basically, ang nag-activate na stiffness dyan is 12 EI over HQ. Something like that. Now, this is our SMAT code for that. So, in-input natin yung height of the columns and this is the corresponding inertia nung frame. So, basically that's the inertia of this whole frame. So, ano yan, kumbaga inertia ng first story, second story, third story, and then fourth story. Okay, so how do you achieve that? Remember, inertia is BH cubed over 12. Diba? So, kunin mo yung cross-section nito ng bawat column. Then, multiply mo na lang sa 4. Kasi you have 4 columns that will resist the lateral loads sa first floor. Diba? So, that will be times 4. So, ang cross-section natin dito ay 300 by 500 mm. Okay. So, times 4, you will get this. 12.5 times 10 raised to 9 millimeters to the fourth. Now, itong inertia, elasticity na to is for the concrete. No? Assume na lang ako around 20 gigapascal. Okay? Pero dahil ang units ko dito ay in millimeters and newton, so that's around 20 times 10 raised to 3 megapascal. Kaya naging 20,000. And as you notice, ito yung ating stiffness formula, stiffness matrix for our beam. And that's it for my BU and BB matrix. So dahil may basically we idealized the 4-story building as a cantilever beam. 1, 2, 3, 4. So wherein meron siyang or cantilever column, may lateral load ka dito, therefore ano ang mag-activate na degrees of freedom? Di ba sa beam natin, meron tayong rotation and kumbaga, ito yung beam natin, sorry. So let's say this is node 1, node 2, node 3, node 4, 1, 2, 3, 4, node 5. Pero yung in terms of degrees of freedom numbering, so this is degrees of freedom 1, degrees of freedom 2, degrees of freedom 3, degrees of freedom 4, 5, 6, 7, 8, 9, 10. Right? So, yan yung mga degrees of freedom. But, anong a-activate lang na displacement is itong mga to, or degrees of freedom. Yan lang, di ba? Because we assume an actually rigid slab, no? Or ano. So, sa translation, such that ito yung sway niya na walang rotation, no? Translation lang. Okay? So, mawawala itong mga to, degrees of freedom na to. So, therefore, 3, 5, 7, 9. So, therefore, ang S matrix natin is 4 by 4. Okay? Kasi we have 4 unknowns, 4 lateral displacements. Right? So, you can now imagine sa K1, ang code ng K1 is, diba, 1, 2, 3, 4. Ang K2, ang code ng K2 ay 3, 4, 5, 6. 3, 4, 5, 6. And anong ma-activate sa K1 is only 3. Ito lang. Diba? So, that's why this is 3. Sa K2, ang ma-activate is 3 and 5, which is ito. So, that's why this is first and third. So on and so forth. Ganun din sa third member and then sa fourth beam number 4. And then yung placement nila sa S matrix. So our S matrix is 3, 5, 7, 9. So si 3 is nasa first, right? Si 5 is nasa second. Si 7 ay nasa third, and then si 9 is nasa fourth. Okay? So that's a 4 by 4 stiffness matrix or structure stiffness matrix. So once after that, okay, and this is my corresponding, pag kinalculate mo yan, this is my corresponding stiffness matrix, which again tell us that this is symmetric. So stable siya. Okay? So symmetric. And these are the forces na, of course, yung mga lateral load applied sa model, which corresponds to degrees of freedom 3, 5, 7, 9. Okay? And these are the corresponding displacement. So therefore, if we plot this, ito yung ating apat, no? 2, 3. Yan. So, yung lateral sway nito is 1.26 mm. Ito is 2.16. This is 2.88. And this one is 3.33. Okay. So, basically, ganyan yung result nung sway frame analysis natin. Okay, and if you check on STAAD, so basically that's 3221. And loading. Yan. This is post-processing, and when you check the displacement here, it's 1.27 mm. Which is almost the same. Dito ay 2.2. We got 2.16. Next is ito. Node 8. 3 mm. We got 2.88. And finally, 3.5 mm. So we got only 3.33. Okay, so may konting discrepancy because again, simplified yung stiffness matrix natin. And of course, in in reality, in typical design naman, ang mga ranges ng displacement talaga, lalo na sa mga low-rise building, nasa 10 mm lang yan, 10 to 20 mm, ganyan. So, very minimal na lang yung pinag-uusapang lateral displacements talaga. Okay, so with that, we were able to show that using just beam matrix formulation, you can approximate the sway of say low-rise building. Right?